Welcome back. In the previous video, we reviewed some of the similarities between solving higher order linear ODEs and solving higher order linear difference equations. Let's go back and make some of that a bit more concrete and give some examples on how you might do that. So the first thing you might notice is that the form of our linear ODEs is really quite similar to the form of the linear difference equations when you write them in the right way. Now, notice that I made a couple changes to notation, and so hopefully these don't get too confusing. For example, in the previous lectures, we may have written something like ak of t x sub t plus k plus dot 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 plus a1 of t x sub t plus 1 plus a naught of t x sub t is equal to b sub t. But the problem with that notation is then our t dependence for x and b is in the subscript, whereas our t dependence for our coefficients are in the parentheses. And that's just a little bit confusing and also makes it a lot more complicated when we want to use the subscript index for different linearly independent solutions. And so for that reason, we're not going to use this notation. We're going to try not to use this notation as much anymore. And it looks like the book also has been moving away from that notation. And instead, we'll use the notation that also makes it a bit more similar to the notation over for linear ODEs. And remember that when we're working with these linear ODEs, we can expand that out. So this is also equivalent to ak of t dk over dt to the k, x of t plus dot 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 plus a1 of t dx of t dt plus a naught of t x of t is equal to b of t. And so the dependence of x on t is implicit, even when we aren't necessarily writing it out. And in the rest of these notes, I actually write it out sometimes explicitly and sometimes not explicitly. You'll see people moving back and forth between that notation depending on how much attention we want to call to the fact that x is dependent on t. In our case, that will generally be understood, but if it's ever ambiguous, you should use x of t instead of just x. I'll be using one notation on one side and the other on the other, but you should see them as entirely equivalent. Okay, so that's just a quick notational difference. We also then talked about finding k linearly independent solutions to the homogeneous equation where we set b of t equal to 0. Now, this here is just the principle of superposition, which we talked about briefly in the context of first order, linear equations, both differential equations and difference equations. And the reason that you can add these together is because when you put these terms in, if you have, let me expand this out a bit. Hopefully I can get, oh, that's not the expansion button. Hopefully I can get the right layer. Oh, I think I missed my k's. That's all right. So let's put our k's back in there. That's a k, that's a k, erase those there. And the reason that we can take these linear combinations, let's extend that out, is that whenever you plug in, suppose you had some linear combination of two of these, just to make life easy. So suppose you had some solution, some proposed solution, x1 of t plus x2 of t, possibly with coefficients. So let's actually just call that x1 plus x2. Well, when you plug it in, because things are linear, you end up with ak of t, dk dt to the k, x1 plus x2, plus dot dot dot, plus a1 of t d over dt, x1 plus x2, plus a naught of t. Actually, let me erase this since. No, I should keep that there. And just be a little bit more careful with writing things out, plus a naught of t x1 plus x2 is equal to 0. But you'll note that because of linearity, we can collect together all the x1 terms and all the x2 terms. So this here is entirely equivalent to saying that, let's see, let me write it all out, that ak of t dk d to the k over dt to the k x1 plus dot 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 plus a1 of t d over dt x1 plus a naught of t times x1 is, and then we've collected those terms together, so we've collected all the x1 terms, and we can collect together all of the x2 terms in the same way. So that's d to the k, dt to the k, x1 plus dot 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 plus a1 of t d dt x2 plus a naught of t x2, and that's just by linearities, is equal to 0. Or rather, if we plug that in, and this is clearly true because each of the individual things, x1 and x2 are individually solutions, so x1 and x2 are solutions. Since each one is individually a solution, you know that the stuff in each of the set of parentheses obviously has to be equal to 0, because they're solutions to the homogeneous equation. And similarly, over here, you get the same sort of behavior, because you have, let's see, again, x1 plus x2. Let's just use that one as an example, and it also, the same thing applies if you multiply it by a constant. And that linearity, the constant just falls right out, and you get the same behavior. Actually, let's do it the other way, just to illustrate that. So let's suppose we had cx1, to show that that clearly is also an example. Well, when we plug that one in, you end up with ak of t x, that's cx1 of t plus k plus dot 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 plus a 1 of t cx1 of t plus 1 plus a naught of t cx1 of t, which is equal to, just pull the c's out, ak of t x1 of t plus k plus dot 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 plus a1 of t x1 of t plus 1 plus a1 of t, a naught of t, that should be an a naught, x1 of t. And obviously the thing in these parentheses is equal to 0, so that's also equal to 0. So in this case, multiplying by a constant, or summing up together different linearly independent solutions, or even the linearly dependent solutions. The linear independence actually doesn't matter for that part. All it matters is you need linearly independent solutions if you want to get a full set of the general solutions. And so that explains why this is true. And so you can take linear combinations, and that gets you a solution to the homogeneous equation. It turns out that a kth order linear difference equation, or kth order linear differential equation, ordinary linear differential equation, has a family of solutions with k arbitrary constants. And so we know that this actually is a general family. Yep. Okay, so moving on from that, let's see. Then we specialize to the case where we're talking about constant coefficients. So in this area, we talked about a as a function, all the AIs as functions of t. Those don't necessarily have to be functions of t. Well, I mean, they have to be functions of t for it to be linear. But we can impose an even stronger constraint that they are functions that they don't even depend on t. They're just constants. So here we're saying that if these things are identically equal to some constants, then we can use something called the characteristic equation. And since we wrote these two in the same form, the characteristic equations are actually identical. So they're just k lambda to the k plus dot 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 a1 lambda plus a naught is equal to 0. What's different here is that we end up with different basic linearly independent solutions. So in the case of our differential equations on the left, things are mirrored for me. On the left, we have that t to the beta e to the lambda t is a solution to the homogeneous equation. Whereas on the right, we have that t beta lambda to the t is a solution. So in the case of ordinary differential equations where we have continuous time, we end up with a power of e. Whereas with the discrete time, we end up with just a power of lambda, as opposed to the lambda being in the exponent on the left-hand side. those of you who maybe have a bit more of a background in, say, finance should hopefully not be surprised by this sort of idea, because this is the difference between continuous compounding of interest versus compounding, say, quarterly or yearly in discrete chunks. And that is actually exactly the same phenomenon. So now, I wrote this in a sort of general way, t to the beta e to the lambda t, where beta is is an integer that is between 0 and the multiplicity of lambda minus 1. And so if a solution has multiplicity 1, so if it's if it's 0 of your characteristic equation only once, then it's just beta is equal to 0 and t to the 0 is equal to 1, and so you just end up with e to the lambda t. So this is the typical situation. In the case where you have multiple copies of that 0 of your characteristic equation, then that's when you need to start adding in the t's. Now, you might be wondering, where do these things come from? So, if you are paid attention in your differential equations class, that should be something that you learned in that class. But let's just quickly give a hint as to where it comes from. And one easy way of seeing this for the case of ordinary differential equations is just to use something called the differential operator. So if you go back up here, d over dt here is a differential. You can think of it as a differential operator that you're applying multiple times to your x function. So if you come back down here to our this area, you can rewrite our original equation when we have constant coefficients as something like this. So you have a to the ak. This is a constant now. Let's say our differential operator is d to the k, applied to x plus plus a1. You apply a differential operator just once to x plus a naught times x is equal to 0. And so now, if you then factor out the x, basically, you end up with something like ak d to the k plus plus a1d. This depends on the linearity of the differential operator, and so we won't go into this in too much depth, plus a naught applied to x is equal to 0. And you'll notice here that this is precisely the characteristic equation. And so if you have a root of the characteristic equation, you can factor the characteristic equation. So here we're going to factor the characteristic equation. And let's say, suppose that lambda is a root of multiplicity m of lambda. So then you end up with something. I don't know what this is, so I'm just going to put in something. And we're going to factor this out. So you're going to end up with d minus lambda to the m of lambda x is equal to 0. Okay? And so, in order, what we want is we want to find a solution that corresponds to this. And so, if we want a solution to the entire thing, then we can also just find if we can just set this part equal to 0, well, then it doesn't matter what's on the left-hand side, because then the entire thing will be equal to 0. So, want this to be 0. Well, if we want that to be 0, then we can just look at that version of the equation. So that's just going to be d minus lambda m to the lambda x is equal to 0. Now, here, life is a little bit easier. And one of the nice things is that we have I'm going to make use of the exponential shift theorem. If you are not familiar with this, you can find this, let me mention it. So, exponential shift theorem, which is theorem of 24.56 in Tenenbaum-Pollard, which some of you will have used as your textbook in your differential equations class. Tennenbaum-Pollard, which then lets us conclude that this thing here, if x is equal to u e to the ax for some value a, actually we already know what we want it to be, so we're just going to say this is equal to u e to the lambda x, len d minus lambda to the m of lambda, or any polynomial function of the differential operator, is applied to u e to the lambda x is going to be equal to e to the lambda x times this polynomial of d plus lambda. Sorry, a polynomial of the polynomial applied to d plus lambda, which is then going to be equal to just putting this in here. This is going to be we've shifted it, so now it's just d applied to the m of lambda applied to u. Okay? And now that we've stated that, well, we know that the, where am I? That is equal to, in order for this to be equal to 0, we need d to the m of lambda u to be equal to 0. But here u can be any polynomial operator with any nth order differentiable function. Oh, sorry, kth order differentiable function. So u is equal to let's see, what constants haven't I used? Let's use c1, and here we're, oh sorry, that should be lambda t, not lambda x, because I'm using the wrong variables. Lambda t. So let's say this is c1 t to the k minus 1. Actually, no, that shouldn't be k. Let's say this is m of lambda minus 1 plus, let me change my coefficient slightly, c m of lambda minus 1 plus c m of lambda minus 2 t to the m of lambda minus 2 all the way down to c1 t plus c naught. And clearly that works because you're just applying the differential operator repeatedly to a polynomial of sufficiently low degree. Which is a long-winded way of justifying the ansatz. The easier way of doing this is you just plug in the guess and check that it works, and you'll see after some amount of computation that this does, and therefore this t beta e to the lambda t is a solution to the homogeneous equation. And I'm not going to bother with doing the full derivation on this side over here, but the derivation has a similar flavor. And lucky for you, because other mathematicians have already done this derivation, you can just guess this as the answer, and it will be correct. Things to watch out for include the fact that you need to really pay attention to the multiplicity of lambda. So instead of doing the proof on the right-hand side, let's actually just solve an example problem. And that should hopefully illustrate the practical application of this kind of result. So let's see. Let us consider. Yeah, let's actually do one that includes complex roots, since that'll make life slightly more complicated. Let's consider example 1.7 in Linda Allen's textbook. So here we have a third-order homogeneous equation. So it's going to be x of t plus 3 plus x of t plus 2 plus x of t plus 1 plus x of t is equal to 0. So now this has a very simple characteristic equation. So the characteristic equation is just lambda cubed plus lambda squared plus lambda plus 1 is equal to 0. Okay, so what are the eigenvalues? Well, let's factor this out. So this is lambda plus 1 times lambda squared plus 1 is equal to 0, which implies that lambda is equal to minus 1 I or minus I. So now that we know the eigenvalues of the characteristic equation, we also know three different linearly independent solutions. So what are they? So we have independent. Oh, let me go switch out eraser. We have independent solutions: minus 1 to the t, I to the t, and minus I to the t. So now minus 1 to the t is nice and straightforward. However, I to the t and minus I to the t, while they are complex solutions, we often want real solutions when we're actually trying to model a biological system. So how do we do that? Well, one thing that you should notice is that I is equal to e to the pi over 2 times I. And you can see this by just drawing out the unit circle in the complex plane. And you notice that if you go up to I, that angle here is pi over 2. And we know that minus I is equal to e to the minus pi over 2 I. Okay, so then we can rewrite those as, I to the t is equal to e to the pi over 2 it, and minus I to the t. Oh, actually, I should put the minus I to the t in parentheses. Minus I to the t is equal to e to the minus pi over 2 it. Now, as you recall, okay, let me scroll up so you can actually see that. So now, as you should recall from your knowledge of complex arithmetic, we can use Euler's identity. So that implies that e to the pi over 2 it is going to be equal to, what is it? Cosine of t times pi over 2 times t, 2 times t, plus I sine of pi over 2 times t. And similarly, e to the pi over 2 it minus pi over 2 it is equal to cosine of pi over 2t minus I sine of pi over 2t. And so this implies that we have another two linearly independent solutions. Cosine of pi over 2t t, and sine of pi over 2t. And these are both nice and real. And so this implies that a general solution is to this, to example 1.7, is then going to be x sub h of t is equal to some constant, let's call it c1 times minus 1 to the t, plus some other constant, let's say c2 times cosine of pi over 2 times t, plus some other third constant times sine of pi over 2 times t. And so the trick here is whenever you end up with a complex root, then you just need to write it out in exponential form, and then that allows you to then use the Euler's identity to get a set of real solutions instead of the complex ones that we started out with. More generally, let's write that down. So this is on page 10 of Linda Allen's textbook. Let me actually give this a bit more space. So this is page 10 of Linda Allen's textbook, and is case 3. So this is case 3. Then what we have is that, so suppose that lambda 1 and 2, suppose lambda 1 and 2 are equal to a plus or minus ib, which is then equal to, if you write it in polar form, that's equal to r times cosine of phi plus I sine of phi, where r is equal to the square root of a squared plus b squared, and phi is equal to arctan of b over a. And so then we have that we can have a set of general solutions which are r to the t cosine of t phi plus, so some constant c1 plus that, plus some constant c2 times r to the t sine of t phi. And luckily in this case for the example above, r was equal to 1, so we didn't have to worry about that part of the eigenvalues. Okay. So hopefully there aren't any more questions on that, and we can move on to finding any solution xp to the inhomogeneous equation. Why do I have in hog? That should be in home. So let's write that in. Inhomogeneous equation. And so for linear ODEs, we have the method of undetermined coefficients, we have variation of parameters, etc. We're only really going to talk about method of undetermined coefficients. Like I said in the previous video, there is also a variation of parameters for linear difference equations, but we're not going to spend too much time on that. So, how do we guess these solutions? Well, you just have to provide an ansatz in the same way that you did for the linear ODEs. Let's pick an example. Let's see that. Let's suppose that we had our, let's continue the example from above, actually. So, what was their example? We found the homogeneous solution to example 1.7, where we had x of t plus 3 plus x of t plus 2 plus x of t plus 1 plus x of t is equal to 0. What if it's not equal to 0? Oh, sorry. Yeah. So what if it's not equal to 0? So let's suppose that we had x of t plus, let me change the notation, x of t plus 3 plus x of t plus 2 plus x of t plus 1 plus x of t. Let's say that's equal to 4t instead. So on the right-hand side, we have a polynomial. And we might guess that the particular solution is also a polynomial of, and so guess that we have an xp, a particular solution that is a linear polynomial in t. So we guess that has the same form, so that's k1 of t plus k2, and then we plug that in to see if things work. So plug it in. And when we plug it in, what we find is that we get, let's see, so if we're plugging that in, if we plug in t plus 3 in, so that's k1 times t plus 3 plus k2 plus k1 times t plus 2 plus k2 plus k1 times t plus 1 plus k2 plus k1 times t plus k2 is equal to 4t. So if we simplify that a bit, that gives us that 4k1t plus 6k1 plus 4k2 is equal to 4t. And, sorry, I keep on running out of space. So, when we simplify a bit, we get that. And if we equate the coefficients, so what we need to do is, well, what coefficients have t in them? Well, we have this 4k t, and we have 4t. So that implies that 4k1t is equal to, sorry, that should, there should be a k1 there as well, is equal to 4t, which implies that k1 is equal to 1. And we also have that 6k1 plus 4k2 is equal to 0. Well, we know that k1 is equal to 1, which then implies that k2 is equal to minus 3 halves. So therefore, we have a particular solution, xp is equal to, that's t plus, t minus 3 halves, which allows us to get a general solution by the principle of superposition. So the general solution here is going to be x is equal to xh plus xp, which is equal to, where were we? We have several different solutions. So if we copy the homogeneous solution up here, let's copy that. Copy and paste. We have all these different so the general solution plus t minus 3/2. And if you had initial conditions, you could plug those in and solve for the three coefficients here to get a particular solution, a different particular solution to the equation where you set the right-hand side equal to 4t. Yeah, so it's very similar to the method that we used in ordinary differential equations, except there are some slight differences in the form of the solution to the homogeneous equation, as well as sometimes when you plug in the ansatz into finding the particular solution, the mathematics is slightly different because instead of taking derivatives, you're plugging in t plus 2 or t plus 1 or t plus 3 instead in for t. Yeah, and the last part of it was just looking at the asymptotic behavior. So you notice that in each of these general solutions, you have some constant times something that grows exponentially. And when you have things that grow exponentially, what matters is how big that exponent is. And so all we're saying is that with the dominant eigenvalues, that is the biggest exponent, and so eventually that will dominate the behavior over all the other ones. If all the eigenvalues are smaller than 0, well, then the exponential part of the solutions all converge to 0. Yeah, so that ends this part of the video. Next time we will be talking about first-order linear systems, and this will explain why we keep on using this eigenvalue terminology, because it turns out there is a matrix whose characteristic polynomial is exactly the characteristic polynomial of these higher-order linear difference equations or linear ODEs. I will see you in the next video.